Light travels at a finite, measurable speed. In a homogeneous medium, it moves in a perfectly straight line. Ray optics models light strictly as a geometric entity, a straight vector navigating physical space. To build instruments that manipulate these rays, we have to mathematically track exactly what happens when those straight vectors hit a physical boundary, like a curved piece of glass. That requires a rigid coordinate system. In optical engineering, this is the Cartesian sign convention. We define the pole, or the exact optical center of a surface, as the absolute zero origin. In this diagram, we see the primary rule of the convention. Distances measured in the same direction that the incident light travels are assigned a positive value. Distances measured opposite to the incoming light are negative. Heights follow the standard y-axis, positive above the principal axis, negative below. By locking every physical distance to this single geometric grid, we can translate the physical behavior of light into predictable, universal algebraic formulas. Let's apply this coordinate system to a concave spherical mirror. For paraxial rays, light rays traveling very close to the principal axis, the focal length is always exactly half the mirror's radius of curvature. Here in this 2D cross-section, a paraxial ray travels from an object, strikes the mirror, and reflects to form a real, inverted image. This geometry creates two pairs of similar triangles. By equating their ratios, we establish a direct proportional relationship between the object distance, image distance, and focal point. Because they sit against the incident light, their Cartesian signs are negative. Plugging those values into our ratios yields the universal mirror formula, 1 over v plus 1 over u equals 1 over f. This also gives us linear magnification, calculated as negative v divided by u. If the resulting calculation yields a negative number, it acts as mathematical proof that the physical image is real and inverted. Opaque mirrors reflect light, but transparent boundaries refract it. When light travels from a denser medium, like water, into a rarer medium, like air, its path bends according to Snell's law. Because the light is entering a medium with lower optical density, it accelerates and bends away from the normal line. The angle of refraction is physically larger than the angle of incidence. In this diagram, as we widen the angle of incidence, the refracted ray approaches the surface. The specific input angle that forces the refracted ray to hit exactly 90 degrees is the critical angle. The geometry breaks down, and the light skims perfectly along the boundary. If we push the angle of incidence even a fraction of a degree past that critical limit, refraction becomes impossible, and the result is total internal reflection. This photograph shows the glowing tips of optical fibers, demonstrating light trapped by this exact phenomenon. Engineers exploit this mathematical limit by launching light into a high-index glass core at extreme angles. The light undergoes successive, loss-free internal reflections, trapping the signal inside the medium so it can travel over vast distances. By calculating the precise critical angle, a perfectly transparent boundary can be forced to behave mathematically identically to a perfectly opaque mirror. A standard thin lens is simply two spherical refracting boundaries stacked back to back. To calculate its total power, we process each boundary sequentially. Looking at this cross-section of a convex lens, a ray of light hits the first surface, bends, and projects a virtual intermediate image. The crucial compounding step happens at the back. We take that virtual image and use it as the input object for the second boundary. The ray bends a second time as it exits into the air. Adding the algebraic equations of these two sequential boundaries together yields the lens maker's formula. This formula is the ultimate industrial blueprint. By manipulating the physical curvature of the front and back surfaces and selecting a specific glass density, an engineer can manufacture a lens with any desired focal power. In a triangular prism, the refracting surfaces are intentionally non-parallel. Instead of focusing to a point, the entire beam path is shifted. The difference between the incident trajectory and the final exit path is the angle of deviation. But the refractive index of a medium is not perfectly constant. It varies slightly depending on the exact wavelength or color of the incident light. Because of this variation, shorter wavelengths like blue and violet slow down more and bend at sharper angles than longer red wavelengths. This forces white light to split into a spectrum inside the prism. Optical geometry is inextricably linked to the frequency of the light being manipulated. Any precision engineering model must account for this chromatic dispersion. The human eye is a dynamic lens system. It continuously alters its focal length, a process called accommodation, to cast a sharp image onto a fixed screen, the retina. Myopia, or nearsightedness, is a geometric mismatch. The physical depth of the eye is too long for its focal power, causing the image to resolve in the fluid before it reaches the retina. The mathematical fix for myopia is placing a diverging, concave lens in front of the eye. This alters the incoming angles and pushes the focal point backward to hit the retinal wall. Hypermetropia is the inverse problem. The focal point falls behind the retina, requiring an optometrist to calibrate a converging, convex lens in these mechanical trial frames to pull the focal point forward. Medical corrective lenses are the precise algebraic balancing of two distinct lens formulas working in tandem. Linear magnification calculates physical height, but for microscopic details, this metric fails. The human eye has a strict physical limit, the near point of distinct vision, roughly 25 centimeters. To evaluate instruments, we use angular magnification. This measures how much wider an image forces your field of view open, compared to viewing the raw object exactly at that 25 centimeter limit. This diagram of a simple microscope illustrates the math. By placing an object inside the focal length of a convex lens, we generate a highly magnified virtual image. Notice the angle subtended by the virtual image compared to the original object at distance d. By forcing this virtual image to sit exactly at the eye's near point of -d, we squeeze the maximum angular magnification out of the system. The simple magnifier is a geometric hack, expanding incoming angles to bypass our biological limitations. Because a single lens has physical limits, achieving extreme magnification requires engineers to compound the math by stacking lenses in series. In a compound microscope, an objective lens creates a highly magnified real image. The eyepiece then treats that image as an object, magnifying it angularly. A telescope solves a different problem. The objective lens, or in this case a massive primary mirror, doesn't magnify. It gathers parallel light from infinity and compresses it into a single focal point, providing a concentrated light source for the eyepiece to examine. From the simplest pair of reading glasses to the largest astronomical observatories, every optical instrument in existence is built by stacking the exact same geometric rules of boundaries, signs, and paraaxial rays.